Hi, Nitin sir. I've made you the host, so you can begin whenever you're ready.
Yeah. Okay. Good evening, everyone. We'll start off with the today topic. In the last class, we were dealing with the physical chemistry. Now we have a bit continuation of chemistry in the form of inorganic. We are going to have the first session of inorganic today, which is more important. And then next we have purely theory session on inorganic, that is on metals and non-metals, their preparation. Okay. So what we'll see is that this topic starts from the generation of cathode rays. Now, what has been done here is in when we were talking about this thing in early 1850. Okay, towards early 1850, what happened? People started doing experiments based on, and they started using cathode ray tube. So they started cathode ray tube and they started. So what I have given you an explanation about what is a cathode ray tube. It is basically a glass containing two thin piece of metals. Okay, those are known as electrodes. Okay, so we have cathode as well as anode here. These are very thin. When we are talking about their dimension, they are thin, cathode and anode. The electrical discharge to the gases could be observed only. It is only possible at very low pressure and at very high voltage. Now, why we are trying to have a very low pressure? The reason is if I'm having low pressure and high voltage, it's basically give you a feeling of vacuum. If pressure is low, it basically will try to give you vacuum, and at very high voltage it's very easy for them to move from one point to another point. That is the reason. The pressure of different gases could be adjusted by evacuation. They have given you evacuation system in this, from where you can collect the, or you can adjust the pressure accordingly, though we try to give the pressure very low. Okay, when sufficiently high voltage is applied across the electrode, how much will be? It's around 10,000 volts. It's around that much high voltage which is applied to this. Current starts flowing because of the high voltage. What will happen? There will be a potential difference. When there will be a potential difference, there will be full flow of current. Okay. Now, what was observed there is, when this have been done, the high voltage is given and at low pressure, what was observed, that current starts flowing through a stream of particles moving in the tube from the negative electrode to the positive electrode. This was observed from, you can see this shining kind of thing. This is being observed is that from negative side starts moving to the positive side. Okay, and how we got to know that there is something being observed here, that we had a fluorescent screen over here, which is normally made up of zinc sulfide. So on this we can see few shadows being observed. So from this we came across with the fact that yeah, there is something, some particles are moving in that, and because it is being observed on this part, so we understand that there is a motion from negative side to the positive side. These particles were known as cathode rays because they had come out of the cathode ray experiment, or they were simply known as cathode ray particle as well. Okay, now the flow of current from the cathode and anode was further checked. What we checked is we made the hole, or you say it as a slit. Okay, we try to give a very small hole, because small hole will be small, light will be passing through with a higher intensity. When there will be a small hole, the intensity of the light which is passing through it, it will be normally higher. And this was observed on a phosphorescent material, zinc sulfide. Phosphorescent materials are those materials on which if the light falls, they glitter, they shine. So we can observe that you were able to find, you see the dots over here that were giving that, yeah, there are some particle which is striking over there. When this rays after passing through anode strike the zinc sulfide coating, a bright spot on the coating is being developed. So now what happened throughout here is the two things. The first thing which is important for you over here is, this is only in data for reading which you are saying. What is important is it is at very low pressure and very high voltage around 10,000. The reason is to create a vacuum inside, because if there will be a vacuum, if the pressure will be low vacuum, then there will be like lowest, there's chances of collision between the particles will be very less, or you can say it is negligible, because in the vacuum the motion will be not that much fast, so collisions will not be there. High voltage, because the motion can be the proper motion will be there from your cathode to anode, and there will be enough amount of electron coming out from the cathode to anode. That's the two reasons. Second thing, what finally was observed, that cathode ray from the cathode electrode, there is something passing through anode, and it was observed on the screen by taking phosphorescent material. For here it is zinc sulfide. So wherever that particles which are coming out from the cathode through anode, they were striking, there was a bright spot being observed. So they were getting to know that yeah, something is striking that particular thing, something is coming out of the cathode, because it is coming out from the cathode electrode. So they have said it as cathode rays or cathode ray particle. Later this only have been named as what? As, because it was negatively charged particle, later this was named as electron. Okay, so what are the few results which was shown? The cathode rays start from cathode and they move towards anode. These rays themselves are not visible, but their behavior can be observed with the help of certain kind of material. That's why we are using fluorescent and phosphorescent light, because you can't see them, they are not visible. That's why we are just using screen to find out, yeah, okay, this thing is happening. Okay, so in this case, what we have is Zn sulfide. Okay, television pictures tubes are cathode ray tube. This is what is there, which is not that much important. You have to know what that much only you try to remember. Cathode rays, what is supposed to be remembered is it is done by using cathode ray tube. Cathode ray tube is basically a glass material. In that you have two electrodes made up of metal. One is cathode, one is anode. Cathode is negative, anode is positive. When a situation where the pressure is kept low and very high voltage in and around 10,000 voltage is supplied, the electrons or the cathode, from the cathode ray you can see a movement of a beam through anode, and it is observed on ZNS, that is a fluorescent or phosphorescent screen. Why we have kept the voltage high and pressure low? So that it can give you a condition of vacuum which will lead to lesser collision and more ejection of electrons at a faster rate. That is what is. Now what is here is in the what, so we said that it is not visible. So how we have able to find it out is in the absence of electrical field or magnetic field, this rays travel in a straight line, normal behavior of electromagnetic waves. In presence of electrical or magnetic field, the behavior of cathode rays are similar to that expected from a negatively charged particle. Okay, that's why they said that the charge which is, or the particle which is coming out of cathode ray is a negatively charged particle, and later the name to that was given as electrons. Okay, the characteristics of cathode ray, they do not depend upon the material of the electrode and the nature of the gas present in the cathode ray tube. For anode, this is depending. When I'm talking about protons, no, that time this will be there, but the characteristics of cathode rays or electrons, they do not depend upon the material or electrodes of the nature of the gas present in the cathode ray tube. Simple thing is, if you are taking anything, if you are taking sodium, what happens is sodium is getting converted to Na plus by losing one electron. So this electron, irrespective of anything, what happens here is if there is sufficient amount of light is striking the surface of metal, ejection of electron will happen. That is what we say as threshold frequency or threshold wavelength, whatever you say, or threshold energy. So here what happens, irrespective of what material you are using or we are trying to use which kind of electrode, if sufficient amount of energy is being fallen on to the metal surface, ejection of electron will happen. That's what is a normal trend. Okay, now you have several models for deciding about this thing. The most important for you was this thing, which from where the questions can be asked, is Rutherford's model. Now Rutherford's model was what? See, Rutherford model was basically, see, Rutherford was not like a poor person. He was having a well-equipped lab, because the thing which he was using here is can be not borrowed by some, but he was basically what? He was a person who was working under J.J. Thomson, who did this experiment, the last experiment which we studied, cathode ray experiment. The cathode ray experiment was done by J.J. Thomson. He was working with him. So what Rutherford did later is to find out whatever J.J. Thomson had said, he did an experiment. What he did is he took a material, that is radium, source of alpha particle. He took a alpha particle which is nothing but it is helium nucleus. So he took the alpha particle, and through this he allowed the alpha particles to pass through. The hole here is very small, and in place here what he had kept thin gold foil. This is very, very, very thin. It is a nanometer. Nanometer is basically 10⁻⁹ meter. Okay, and it allowed this alpha particle to bounce. Why it have kept thin gold foil? Because there will be less deflections and you can get more exact values. So what it did it here they have kept thin gold foil here, and the alpha particles were allowed to strike on the surface. So what happened is, what was observed here, see now on this is also ZNS kind of material, phosphorescent or fluorescent, whatever you say, both stand for the same thing. So what happened, alpha particle striking here, and this was observed that on the screen, on few places you are observing there some bright spot. What they were observing, that most of the light was passing through directly from the gold foil. There were very few which were getting deflected, and there were very few which were getting deflected exactly like, say, if I have something in this situation, so if the alpha particle is going like this, somewhere here, what was happening is they were exactly getting, so like this it is coming, and like this only it was coming back. In most of the places, it was just passing through, and then in very few places it was getting deflected to smaller angles. This was he observed. Now this is how the further experiment, after doing this experiment, what he observed is, so he gave few conclusion based on this, because what he said that almost 1 out of 20,000, 1 out of 20,000 is the ratio of the particles. When I'm taking alpha particles, 1 out of every 20,000 was reflected back exactly around an angle of 180 degree. That means it retraced the same path. Okay, now as we all know, while doing the experiment only, he knew that alpha particle is basically positively charged. So now what he got to know, that because it was getting reflected back, so he assumed that there is something which is present at the center which has to be of positive charge, because the particular thing, that is helium, that is alpha particle, when it is striking at that position, it is retracing the exact same path. Now again, you can see there is smaller deflection when it is nearer to the center of this, and there's most of the particle is passing through. So what he said is that most of the part in a particular atom is a vacant part, and there is something at the center which is occupying a very small part of it. Almost you can say that if you're talking about a saucer ground, if you're talking about a cricket ground, the tennis ball, that much size is basically the ground is atom and nucleus is of that size. So further he said, what is there something which is present in the center which have to be of the same nature of the charge of alpha particle, that is positive charge, because it is retracing exactly same path from which it is coming. So this all he concluded, and later they gave the name as this, the name for this is given as nucleus. And with the part, now till that time there was no discovery of neutron. Later, neutron came later, when in 1932. It's a very recent discovery. In 1932, neutron discovered by James Chadwick. What they said is, even after they did the calculation, they found there is something present in the. So they got to know proton was discovered, electron was discovered, because proton when they discovered, electron they discovered, they got to know they have this have -1 charge, this have +1 charge. So now this was electrically neutral. The atom was electrically neutral, but still when they were comparing the mass, so when they was comparing the mass, there was some shortage still. So what they got to know is, later on after the discovery by James Chadwick, he said there is something which is present in the nucleus which is chargeless, which doesn't have any charge. It have a mass which is almost equivalent to proton. So in 1932, that was discovery of your neutron. For you, what is important is, for you, the important part is cathode rays experiment and Rutherford model. So Rutherford model, they did this. That was its observation. Okay. Further, we have the conclusion. So what he observed here is, see, I said you the most of the alpha particles pass through the gold foil undeflected. A small fraction of alpha particles deflected by small angle, and 1 in 20,000 bounce back, that is a deflected nearly 180 degree. That is one part. So what in the further thing, this was his observations. So based on observation, he gave some conclusion. So this was his conclusions. What he concluded is, most of the space in the atom is empty because it is going undeflected. A few positively charged alpha particles were deflected. So they got to know that at center you have a repulsive force, and based on that, but what they compared that it's of a very small volume. Okay, Rutherford calculation showed that volume occupied by the nucleus is negligibly small, as the radius is what? Radius of the atom is, this has to coming like this. This is 10⁻⁻10 meter, the radius of atom. And what is radius of nucleus? Is 10⁻⁻15 meter. So this you have to remember. This ratio is also, maybe they can ask you the ratio of nucleus to the ratio of atom, or maybe radius of the atom to the radius of nucleus. Okay. So up to this, okay, there's no problem with this. Now, what problem happened with all this is everything was fine. What he said is what Rutherford again said, like that was told, the same thing was told by Thomson, and the same thing Rutherford proved as well. He said what is the electrons. Here he said that at the center you have nucleus and electrons are moving around the nucleus. Electrons are moving around the nucleus in a circular orbit, in a circular path. Yes, he said that they are moving in a circular path, which is known as orbits, or you can see it as energy cell. He said that. But now what was the problem here is, as he said that electrons are moving around this thing. So as we all know that electron is a charged particle. Fine, electron have a charge. So electron is a charged particle. Now when electron have a charged particle, so according to the Maxwell's law, when you're talking about the any charged particle, so Maxwell's law come into the picture. Maxwell's law says what is? Maxwell's law of what? Maxwell's law of electrodynamics. Okay, which basically talks about a charge in motion. So Maxwell's law of electrodynamics said what is, if a charged particle is in motion. Now, this is the first point. Obviously, charged particle is in motion. Okay, because it is moving, it is in motion. Now it is, see, again, it is a uniform motion, but it have acceleration. More, when we read uniform motion, we say that uniform motion doesn't have an acceleration. But when I'm talking about something which is moving in a circular path, so for something to be uniform motion, when I'm talking that something has to be uniform, I have to check two things. The first point is the velocity should be constant. So velocity should be constant. Second thing should be there will be no direction change. So we should not have no direction change to have a uniform motion. But you can see here that every moment it is changing its direction. So though it was having a uniform motion, the electron is still have some acceleration. Acceleration was there. So what Maxwell said, that any charged particle which is under acceleration, it will start losing its energy. When it is in the motion, it will start losing its energy, and it will, at some point, it will come to rest. It will start losing its energy in the form of what? Electromagnetic radiation. So that was the law of Maxwell's law of electrodynamics. According to Maxwell's law of electrodynamics, if a charged particle is having a motion, having an accelerated motion, then it will start losing its energy in form of electromagnetic radiation, and after some time it will come to rest. When this calculation was done for electron, it came as 10 raised to minus 8 per second, 10 raised to minus 8 second, it should come on rest. But this was not happening. This was not explained by Rutherford. He said that it is moving, but it was not explained by Rutherford. So this was its drawback. He could not explain. Second thing, he could not explain about the spectral line, that why some electrons give energy, or they show some kind of color, but some particular elements don't show, some particular elements show. So all this was not explained by Rutherford, but the major thing is this only. He could not explain about why they have a motion here and they are moving in the circular orbit. They are even accelerated, when why this is not falling in the nucleus. If this is true, then if I say about the electron, after 10 raised to minus 8 second, the electron should fall in the nucleus, but it was not happening. So what is more important for you when I'm talking about this? This is obviously the observation is there, true, but what is more important is the drawbacks of this thing, Rutherford model. This is the first point. And second thing is the ratio of this thing, if I'm trying to find out. So I know that when I'm talking about the radius of atom, it will be 10 raised to minus 10 meter. And when I'm talking about radius of nucleus, it will be 10 raised to minus 15 meter. This is what is important. And this is the fact, 10 raised to minus 8 second it should take to fall the electron inside the nucleus, because it was not happening. Okay, so it was not explained. So when this problems came into the picture, the next thing what came here is everything was explained by using what? Bohr's atomic model. Now Bohr's atomic model is very important for you. Now what he said is, he directly mentioned that, okay, he said what is okay, electrons are moving around an orbit, which is an elliptical orbit, you say. We assumed it to be so what he said, that electrons are moving around the nucleus in certain definite orbits. Okay, electrons, like if an electron is moving here, it will only move in this particular part. If an electron is moving in this, it will only move in this particular orbit. These things are known as what? Orbit. Or these are also known as what? Stationary states. You say it as stationary states, or we even say them as what? Energy level. So what he said, that yes, they are moving, they are charged particles, they are accelerated, but they are not going from one place to another. If some electron have to change their position, if some electron wants to go from lower thing to higher, they have to get excited and go. To get excited, they need what? They need energy. So if they take energy, they can go from a lower shell to a higher shell. And if an electron have to come down, it need to lose energy to come to its ground state. It will lose energy, so it will give energy and it will come to ground state. And that's what is happening. Till there is no absorption or there is no release of energy, they'll stay back to their stationary fixed energy level. They can't change it. Now what he said is, electron which are revolving in the orbit, they'll have an angular momentum. So he gave a value that they'll have an angular momentum, which angular momentum is given by, that is angular momentum will be mvr will be equal to nh upon 2 pi, where n is what? N is the number of the soft shell. Number 1, number 2, number 3, like that. And when I'm talking about mvr, this is what? This is angular momentum. M is mass, v is velocity. This is the radius for this. H is your Planck's constant. So he said what? This was his second point. This was his first point. Second point, he said what is angular momentum is integral multiple of h by 2 pi. So we write it in this form. Now, next thing what he did is derived the things for every particular velocity, radius. How we did that is, he assumed what here is, so there is what we said is, here is the nucleus and here is an electron. So we remember, obviously we have read that electrostatic force is equal to K, Q1, Q2. Whenever there is a two charge in nature, they'll have a repulsive or attractive force. So in this case, what is happening, because they're opposite? So what is here in the center? The charge at the center is Ze. Why I'm writing Ze? Because Z is the number of proton. How many number of protons are present in the nucleus? That, and with one particular electron, what is happening? That force. Now, so this force is known as what? We say it as electrostatic force. In this case, I'll write electrostatic force as K Q1. Q1 will be Ze into Q2, that is E, and that is the radius, whatever is the radius from here to here, whatever will be the distance. Again, when somebody, something, or some particle is moving in a circular motion, it will have a centripetal force which is towards the center. Centrifugal force is away from the center. Centripetal force is towards the center. That centripetal force is given as what? mv square by r. Okay, fine. So then I'm talking about this thing. Okay, so kz is Ze by r square. This will be mv square by r. So what we know is, now we write is, this both have to be equal if the body have to be in motion. So using this, what we did, we derived value for the nth orbit, energy level, velocity. So what is the value for this one? So the fourth point is, the radii for the stationary orbit is given by a0 n square by z, where a0 is the radius, or that is the distance of first. Many people, we can write it in the form of 0.529 n square upon z. This is also possible. Okay, you need to know both the formulas so that they can ask. Now, if you use that formula, you can see that I can write directly that Rn, that is radius of nth orbit, is inversely proportional to z, directly proportional to n value. So I can say that the nth orbit is directly proportional to what? It is proportional to n square, and it is inversely proportional to z value. What is this n? We have read in the last graph, n is nothing but it is principal quantum number. Principal quantum number is the n. Okay. Next thing what is there is we have to find out energies. So energy of the stationary orbit is given by -1312 upon n square z square. This is kilojoule per mole. From here, what I can say, the energy is directly proportional to what? Z square and inversely proportional to n square. You can see this. You can see this. We will use all this when we are solving the numerical, then you'll understand what I'm saying there. Now, when I'm talking about the velocity of nth orbit, that is given by 2.188 into 10 raised to 8 upon z upon n. This is again centimeter per second. Now from here, what I can write that velocity is directly proportional to z, inversely proportional to 1 by. This is what, there's a few values which are supposed to say. Obviously derivations are there. I'll not say derivations are not there, but at present derivations are not needed. So I don't think that you have to get into all that. Whatever is required, that is what is we're going to study. Everything unnecessary you study and you're not able to retain that. That is not good. I just gave you the reason why that is there, but the values what you have to remember, this much is enough. Okay. Next. So with this thing, now if I'm having one particular other thing in this will be what is, we have a very important formula here is number of spectral lines. Now number of spectral line is what, when a particular electron gets excited and move from one particular shell number to another label. So we write the formula for that is n2 minus n, where this is excited, this is final, and this is initial energy label number by n2 minus n1 plus 1 upon 2. This is very important formula to find out number of spectral lines. Okay. Also, when I'm talking about drawback for this, we write what is drawback for atomic model of Bohr's. The first one is it is only applicable for one electron system. One electron system are what? Hydrogen-like system. So you're talking about, as you say it as hydrogen, you say it as helium plus, you say it as lithium 2 plus, you say it as beryllium 3 plus. It is only applicable for one electron system. Second thing is it could not explain Zeeman and Stark effects. This we'll study later. You might have studied as well. Zeeman is basically the effect of a charged particle inside magnetic field, electric field, and Stark is basically in magnetic field. Okay. So this is what is some, you can say that there is some drawbacks. This was which was there in this, but drawbacks normally is not asked for Bohr's atomic model. Questions related to this will be there in your exam in terms of numericals. So we'll just focus on that thing. Okay. Okay, now next term what we have is Mendeleev's periodic law. Now what happens before we go to Mendeleev's periodic law? Before Mendeleev's periodic law, we had many things which came into, they started giving a lot of laws according to the how we are supposed to arrange the elements known. Before that, who was there? We had law of triads. Law of triads was given by whom? Law of triads was given by Dobnier. Before that was law of octaves. Now, what are all these things? So law of triads, if you see, they had given you, say, like for example, they are given in this lithium, sodium, and potassium. So Dobnier said, what is, if you're taking this and you're taking this, these are basically what? This is atomic weight or atomic mass. So when you take the atomic mass of two elements, the middle element will have the average of these two. Atomic mass. So your 39 and 7 is 46, 46 upon. So this 46 upon 2 is 23. So this, he gave this thing. You have example for calcium, strontium, barium, chlorine, bromine, iodine, but it was only limited to very few elements. What was the problem with law of triads? It was only limited to very few elements and it was not applicable also to every element. Plus the problem with this was it's own this thing. Now say if I'm talking about, for example, I'm talking about The same case, if I'm saying here, I'll take it as I'm taking the last group, which is known as what? Which is fluorine, chlorine, bromine, and iodine. Okay, this all is there. Now, when I'm talking about chlorine, bromine, and iodine, so I'll take chlorine, bromine, iodine. This is 35.5. Iodine is something around 127. So when you take the average of this thing, it will come nearer to 80, right? 120, 30, 150, 157, 162.5. So it's something around 162.5 is something around 81.25, but approximately we write it as 80. Okay, that is fine, still acceptable. But what happened now? You consider this three here. So when you're talking, considering this three, what happened? Fluorine is having what? Fluorine is having 9. Again, chlorine you leave, bromine is having 80. You take sum of this is 89. 89 upon 2 will be what? It will be something around how much? 44.5. How much I normally have is 35.5. So what problem happened with law of triad is his own law, Dobnier's own law, was being discarded in the same group. Some 3 elements are following it. The further 3, the initial 3 elements are not following it. So because of this, his own law was discarded in itself, starting itself. So that's why it was discarded. Now, second thing was which one? Law of octave. Now, law of octave said what is? You arrange the elements in increasing atomic mass. 8 elements. So if you say like lithium, beryllium, after that we have boron, then carbon, then nitrogen, then oxygen, then fluorine, and then you had sodium. So what he said that, so this is first element, first, second, third, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8. So what he said that every 8th element have the similar property as the first. So every 8th element, they are repeating the property. Okay, fine. We understood this. This was okay. But then next, when they are moving further, okay. Potassium, then again they had the similar properties, and this you talk about magnesium, similar property. Problem happened what is, when the discovery of noble gas came, it failed because noble gas came in between here. So now this lithium and this argon property was nowhere feasible. It was not coming true. And the second thing was, it is only applicable to 20 number element, that is up to calcium. Second problem. So when all this is done, again parallelly we had Mendeleev as well as Lothar Meyer, who was doing the experiments, but Lothar Meyer started plotting graph which was not that much easy to understand. So Mendeleev's periodic table was, or Mendeleev's periodic law was acceptable. He also did the same thing. What he did is, he allowed all the things or all the elements to combine and form oxide. Based on a formation of oxides, he did what is, he found out valency of those particular elements, and then he arranged them in a particular order. Okay, then he arranged them into the particular order. So he did the same thing. He arranged the all the metals or all the elements which were known that time. He could arrange all the 63 elements which were known that time using this. And what he did is, after arranging, he even left few places, like saying it as he said few, says a ekka silicon or ekka aluminium or ekka boron, like that. He left few spaces while he was arranging them. And later what happened, discovery of this thing. So ekka silicon was given as germanium, aluminum was given as gallium, and boron was taken as selenium. So what he did is, he not even able to arrange all the 63 elements, or the things which were not known also that time, those were also, what was happening was, those were also given space, and later they were discovered and they were put in that. So everything was falling in line. Problem happened what is, there were few arrangement in that, atomic masses, few things. So what he said is, elements will be arranged in increasing order of atomic masses. Okay, atomic masses or atomic weight. Problem what happened is, he arranged few things which are having higher atomic mass before. For example, copper he arranged here, and after copper he gave you zinc. So copper was having a situation here is what in this copper this all were having incomplete shells here. Now when I'm trying to arrange this, what has started happening is, if you see in example, you'll see many things which are having more this thing are having arranged before them. If you have seen the periodic table, in that also you can find it out. For example, there are so many things. If you're talking about cobalt, so if I'm writing cobalt here and after that I'm writing nickel, so the cobalt was coming before, which was having 58.9 atomic mass, and nickel was coming later, which was having 58.7 atomic mass. So this here it failed. Again, problem where it arose is, again say we had TH and Pa, thorium and so polonium. This is 232, this is 231. So now his 232 came before 231. So there were few places where this theory failed. He could arrange most of them. There was no problem that he was not able to arrange. He was able to arrange them. Everything was falling. He could even the two problems could not be solved, that he could not explain anything about isotopes. Because he said what, that we are arranging it in the form of atomic masses. Now what about hydrogen? Hydrogen have what we say, what it have same atomic number but different, so different atomic masses. So deuterium same atomic number, masses is different. This is isotopes of hydrogen, protium, deuterium, and tritium. He didn't say anything about those. If I'm saying that you are giving one place to one hydrogen, what about this two? If you're giving it this to this one, if you're giving them where helium goes, if you're giving this as position, so where lithium goes. So this were the few problems which arose. Later all this problem was solved, which was known as modern periodic table. Using modern periodic table, what we did, we defined, we got the problem solved. So what we did in modern periodic table is everything was kept constant. What they said is the physical and chemical property, this is what is acceptable. Now they did what is Mendeleev periodic table was bit modified. Everything was acceptable. He had given groups, he had given periods, all the things were acceptable. Horizontal line as we'll take it as period, vertical lines will take it as group. All the things were acceptable, which was moved to the modern periodic law or modern periodic table. Only one small changes we had is, instead of arranging them in the form of increasing atomic mass or decreasing atomic mass, what we said that the physical properties, the physical and chemical properties, the physical and chemical properties, okay, they are what? They are periodic function. The periodic function of their atomic number. See here only what difference came into the play. A periodic function is obviously the functions will be repeating after certain interval. That is what is a periodic function. And atomic number. Now we removed atomic mass. We kept atomic number. Now everything was solved. Isotopes, okay. Atomic number. Atomic number. You come deuterium, atomic number. So everything was being arranged when it came to modern periodic law. And this modern periodic law only we have followed till now. This is what is the law we are following at present. So this is the few things which is somewhere important for you to understand for the basics of periodic law, from where the periodic table came, from where the things have started. These are the few things which you're supposed to know. Now we are supposed to read about what? We are supposed to read about the periodic table, which we are following now, from where the most of the questions are going to come. So we'll go to that. Okay. Now you need to be very keen and calm because questions mostly comes from this. We'll go to the periodic law. Now modern periodic, we'll just go to the tables, we'll go to the laws. So periodic properties, before that we'll just see small introduction of this thing. Periodic properties is what we say is when you are moving left to right, we say what? This is periods, which is horizontal line, and we're talking about vertical line, these are known as groups. Okay. Now when I'm moving like this, I have 7 periods. Like this, I have 18 groups. I arrange them in the order of the increasing atomic number. So we have group 1, we have group 2. Group 3 to 13 is known, group 3 to group 12 is transition metals, and then it comes group 13, 14, 15, 16, and 17. We have different names for this according to their behavior. What is the different name? This is known as what? This is alkali metals. These are metals because they have plus valency. Why they are alkali? Because they form a solution which is alkaline in nature. See, there is a difference between base and alkali. Water soluble bases are known as alkali. If there is something which is, we are saying that it is water soluble, then Gautam Kushwaha is saying horizontal is group. Okay, like this is what? This is periods. This is across periods, and this is down the group. Okay. Now, when I'm going about this, this is group 1. Group 1 is alkali metals because water soluble bases are known as alkali, and so they are water soluble and they form an alkaline nature. This is named as what? This is known as alkaline earth metal. The second group is known as alkaline earth metals. Why we say them alkaline earth metals? Because they are found out in they are found out in what? Earth crust, and they form even insoluble water function. So that's why it is known as alkaline earth metal. These are what? These are transition metals. Transition metal, or you say it as bridge elements. Transition metals. Why? Because they have a transition in between. There will be showing a lot of transitions. They have a lot of properties which are very useful, like they form colored complexes, they show paramagnetic nature, they form catalyst. Or catalyst, wherever you see is nickel, palladium, platinum, all this belongs to D block elements, that is from group 3 to 12. Okay. When I'm talking about group 13, this is known as what? This is known as your boron family. This is known as your carbon family. Okay. Obviously, this is known as nitrogen family, but it have a name which is known as pnictogen. It is known as pnictogen. Why it is pnictogen? Because these are normally poisonous in nature. Pnictogen is something which is poisonous. These are normally poisonous in nature. Now, 16 is what? Oxygen family. Name for this is chalcogens. Chalcogens are basically what? Chalcogens are nothing but they are ore forming. Those things which are, so most of the ores you will see from this group. Next, the last one is what? We have halogens over here. We say halogens, why? Because they normally what? They are salt forming. So this is why they get this name. Last is group 18, which is known as what? This is known as zero group, or you say them as inert gases, or you say them as noble gases. So this is somewhere what is there in the arrangement. In between group 3 only, when you go further in group 3, period number 6 and period number 7, we have something known as actinide and lanthanides. We have actinides and lanthanide present here, which is nothing but it is F block elements. Group will be 3 for them. Period will be 6 and 7. Further, when we are we need all that. We'll see that at present all is not needed. But the questions from where it is coming, you'll just read that. Alkaline earth metal, alkali metals, boron family, carbon family. 15 is known as pnictogen because they are poisonous in nature. Group 16 are known as chalcogens. They are ore forming. 17 is halogen, salt forming. Group 18 is zero, inert, noble. Why we say them noble gas or inert gas? Because they are unreactive. Their free state is unreactive. That's why we say them. This is basic when we are talking about periodic table. So now we'll go to the periodic properties. We'll see one periodic properties, and then we'll see the questions related to them. Okay, so the first thing here is the first property which you are supposed to study is atomic size. Okay, so atomic size, the name only suggests atoms. Now, how to find out atomic size? When I'm trying to define atomic size, what will be an atomic size? Just say if I have an uncombined like free state single atom, say helium or something. So what we do is we just take the radius from or the distance from the center to the outermost electron or outermost shell, and that is what is known as atomic radius. Say for this combinations of things like H2, O2, all that, what we do is we just write this, we get the formation, say something like this. What we do, maybe there can be inside as well. So what we do, we take center to center distance. So say this will become distance d of H2, we divide them by 2, this will give me radius of H2. So this is a two-way how we define atomic size. First way is the distance from the center to the outermost shell. Second is what? The internuclear distance between the two particular combined atom. Okay. Now, so every time what we have to see about periodic properties is there is two possibility. Either it can go like this in period, or like this it can come across in the group. So let's take few examples here. Say I have lithium over here, I have beryllium over here, I have boron over here, I have carbon over here, and on this side say I have what? Lithium, sodium, and potassium. So if you see here, what is happening in this is lithium is 2, 1, 2, 2, 2, 3, 2, 4, like this it is going. And here what is happening? It is 2, 8, 1. Here it is 2, 8, 8, 1. So when you see here what is happening, every time there's an addition of extra shell. Here I had how many cells? 2 cells. 2 cells means period number 2. 3 cells, period number 3. 4 cells, so period number 4. So when I'm talking about this cells number, what will be there? Number of this thing represents how many period number that is. So you can see when I'm moving down, there is energy of 1, 2 cells, then again it became 3 cells, then again it became 4 cells. So now what is happening here is there is addition. So what is happening? Distance from here to here, then distance from here to here, the distance from here to here keeps on increasing. So when the distance is increasing, that means what is? Atomic size is increasing. When I'm moving left to, top to bottom. Now, when I'm going to left to right, so now what is happening here is, when I'm talking about left to right, so what is happening here is, proton is present here. So in the nucleus, what is there? In the nucleus, I have total 3 proton. It have to pull 1 electron. Now further I move, 4 electron. It have to pull 1 electron. 5 charge at the center, it have to pull 1 electron. 6, it have to pull 1 electron. So 3 will pull more than that, 4 will pull more than that, 5 will pull more than will. Why I'm taking only 1 electron? Because at a time it will be pulling 1 electron, Ze into E. You just read Coulombic force, Z into, it will be at a time pulling only 1 electron. So if it is trying to pull 1 electron, because of this, there will be a compression in size, there will be a shrinkage in size. So if I want to just summarize all this, how I'll summarize this? There is only 2 ways when I'm talking about what about trends of atomic size. Either it can go top to bottom or it can go left to right. So when it is going to top, when I'm talking about it is moving top to bottom, or it is moving left to right. So when what is happening when it is moving left to right, Z effective, that is effective nuclear charge increases. Effective nuclear charge increases. Because of this, what happens? Force of attraction between what? Force of attraction between the nucleus, positively charged nucleus, and the electron increases. Because of this increases, which leads to the decrease in the size of the atom. But when I'm moving from top to bottom, what happens? Cell number increases. There is an addition of cell. So cell number increases. Because their cell number increases, what happens? Size increases. So this is the 2 thing which is there. This is the 2 things. Definition is done. This is the normal trend. This is the general trend. Now, when I'm talking about periodic properties, we have exceptions here. Always exceptions in chemistry is the thing which creates a lot of issues. Students get irritated, obviously, because chemistry is normally what? It's an experimental science. First, what happens? Whatever we read is experimentally it have done and it have been written in the book. We are not able to see it. Sometimes we are not able to see it, so we don't feel to study it. Though, let's try to bear with it. If you're going higher studies in chemistry or doing research or something, you'll be able to know about everything. Okay. Exception is what? Now, what I'm saying is, for example, if I'm saying is, if I'm taking a group, so for example, I'll take it here, I'm talking about lithium. So after lithium, I go to beryllium, then I go to boron, then I go to carbon, then I go to nitrogen, then I'm going to oxygen, then I'm going to fluorine, and then I'm going to neon. Now, what I said is, if I'm moving from left to right, Z effective increases, force of attraction increases, size is decreasing. But this is an exception that in a particular period, and I'm talking about a particular period. So if I'm moving to first point, exception is what? In the respective period, in respective period, what will happen in respective period? Noble gases will have highest or maximum atomic radii. Now, why this came? Why maximum radii? The reason behind this is because they only exist in uncombined form, and anything in uncombined form will try to stay far away from each other, and it only force here acting is van der Waals force, and van der Waals force is the weakest force of attraction. So in the respective period, this is an exception. Left to right, it was supposed to decrease, but in this, when I'm talking about the last, that is the noble gas, they will have the highest size. The reason of having highest sizes, the only force of attraction present in between them is van der Waals forces, and because of van der Waals forces, what will happen? They will have the biggest size. First exception. Okay. Next. I'm talking about the second exception. What will happen? We'll discuss about 3D series. Okay, so 3D series, the first element for the 3D series, we have scandium. After scandium, we have titanium. Then we have vanadium. Then we have chromium. Then we go magnesium. From magnesium, we go to iron, cobalt, nickel, copper, and zinc. Okay, so now when I'm talking about this, this is 21. So when I'm talking about 21, this is basically D1. This is D2. I am just writing 3D1, 3D2. 3D1, 3D2. Basically, I want to say here, this is okay. So this is nothing but this is zinc. Now this is 3D series I'm talking about. So D1 electron, D2 electron, D3 electron, D4 electron. Okay, so this D will be 5. If you remember Aufbau principle, chromium and copper, two are exception. This is again D5, D5, D6, D7, D8, D9, which is D10, and this is also D10. Because here what happens, because of attaining stability, they try to attain fully filled electron, and they try to attain half filled here. So that's why we have D5 in two places here and D10 in two places here. Now, what is the exception over here? What we studied left to right, the size should decrease, but normal trend says what is scandium again is greater than titanium, is greater than vanadium, is greater than chromium, and then it is now when I'm coming to this point, chromium to magnesium. After this, what you'll find out between magnesium, up to this trend goes normally. Here what happens is you'll find out almost similarity in their size. The size will not change, and further what happened, from nickel you'll find that this is greater, and from copper zinc is greater. Now why this exception is there is, now let's try to draw the d orbital. So if I'm trying to draw d orbital for something, so I'll draw what, 5 in that. So 1, 2, 3, 4, 5. Now, if I'm filling the electron, so up to here, there is no problem. What problem starts from here? Okay. So here 1 electron, 2, 1, 1, 1. So up to this is D5. Now the first problem arises from D6. So say D6. This is D6. Okay. So now D6 is iron. Now in D7 is further what happens here is 1, 2, 3, 4, 5. 1, 2, 3, 4, 1, 2, 3. So this is D7. Now what is happening, problem here is, till they were singly occupied, there was no repulsion between the internal electrons. Now as we started getting 2 electrons in the cells, what happens now? Two forces starts coming here. Which two forces? One is attraction forces because of the nucleus, and which one? Because of the nucleus and the outermost electron. And there is repulsive force which is coming where? Internally between the electrons which are present inside each other. So what happens because of this? What happens when I'm moving from the starting up to here, when I'm moving from manganese, what dominates is here attractive force between this is dominating. Okay, attractive force is dominating. Then further what happens up to this point? Okay, from up to here what starts happening is they are almost equal. They're trying to overcome. The attractive force is trying to overcome dominating force. In this reason what happens, you can write that attractive force overcomes or tries to overcome repulsive forces. So because of that, there's not much of increase in the this. Now what happens further here is your repulsive forces dominates, because now D10 is what? D10 is fully filled. So in this case, repulsive dominates. So this is what is the reason I was talking about. Okay. This is the properties, which is the second exception. I told you the normal trend, and I'm telling you the exceptions. Okay, this is the second exception. Next, when I'm talking you the same thing, we have one more exception here is third exception. Now, if I'm writing the group 13, we write is what is, we have first one is boron, aluminum. Okay. Indium, thallium. This is what is a normal thing. So what I said is normally when you are moving down the group, size should what? Increase. Size should increase. So normally what I'll write is boron will be less than more aluminum than gallium. What is observed there is radius of aluminum is almost equal to radius of gallium. Here what is there? This is 13 and this is 31. What? Atomic number. Atomic, but what we observed that atomic radius of aluminum is almost equal to radius of gallium. Why this happens? Reason behind this is due to poor screening, of 3D electrons in gallium. Now what happens here? 3D electrons are present. So 3D electrons, they have a poor screening effect. What is screening effect? Inner electrons, they try to give shield to the outer electrons. This is what is here said as screening effect. But before gallium getting into the 4p part, you have full 3D10, that is zinc. Zinc is 3D10, and then gallium comes. So here is where we end into 4p1. So this particular d electrons, they have bad skidding effect. Skidding effect of S is best, then P, then D, then F. So because of bad screening effect of D, what happens? They are not able to protect the outer electrons that much. So it gets more pulled towards the nucleus. Because of this reason, what happens? They have almost similar size. Further pattern is same. Boron, more than boron, aluminum is there. We'll also write this thing how when we are reading the ionization energy. So this is the three exceptions. Please try to remember them. Okay. Next property which we are supposed to get into, second periodic property, is ionic radius. Okay. Ionic radius. So when I'm talking about ionic radius, as you see, normal atom will be present. So what will be there? Normal atom means it will be neutral. So it will have atomic radius. Then there is something which is charged, say Na+. So it's an ion. If I'm talking about nitrogen 3-, it's an anion. So that time what the radius will be there, that is known as ionic radius. So same trend will be there, same trend. There will be no trend change when I'm moving from top to bottom. Like when I'm moving top to bottom, so there will be no change. It will be the same. Top to bottom, what will be happening? Cell number increases. Because of increase in cell number, what will happen? Size will increase. In this, there is no discussion. Okay, fine. But problem starts where in this is the first thing. Problem starts where when I'm moving in left to right. Left to right also, when the problem is start, left to right, the problem start when we are talking about isoelectronic species. Now, what is this isoelectronic species? So isoelectronic species is those species which have the same number of electron. So same number of electron. Why the problem increases? For example, say I'm taking example is sodium plus is there, magnesium 2 plus is there, aluminium 3 plus is there. I have all these three. Now if I'm writing number of proton here, it will be how much? Number of proton here is 11, here 12, here 13. How much is the electron here? 10, 10, 10. Now you see what is happening. Now here 11 11 proton will pull 10 electron. Here 12 will pull 10. Here 13 will pull 10. Which will be more strongly pulled? This one. So whose size will be smallest? Aluminum. So I'll write like this. So for isoelectronic species, there can be small confusion. So what we can generalize for isoelectronic species is size is inversely proportional to atomic number. Size is inversely proportional to atomic number. You see here, atomic number is here 11, 12, 13. Whose size will be more? Will be whose atomic number is less. Whose size will be less? Whose atomic number is more. This is what is a normal tail you can remember for isoelectronic species. And the third thing which we are supposed to know in ionic radius, obviously, if you have an particular atom for the same particular atom, the anion radius is more than the parent and then the cation. This is what is a normal trend. So this is the three things which you're supposed to know in ionic radius. Ionic radius, most important is this only, isoelectronic species. Okay. Now next thing which you're supposed to deal with is, I hope you are all are getting it. This all is good. This all is important though. Okay, the third property which you're supposed to deal is ionization energy. Ionization energy. Now, what is this ionization energy? So ionization energy is the amount of energy required. This is amount of energy which is required to remove an electron. The three words should be there. It is the energy. First of all, this is an energy which is required, for release of one electron. Release of an electron from where? From, and this from an neutral. It has to be a neutral, isolated, and gaseous atom. All these conditions should be there when you are looking for ionization energy. The definition says this: the amount of energy required to release an electron from an neutral, isolated, gaseous atom. Okay. For example, if I'm talking about sodium, so sodium normally exists in solid form. So now sodium, okay, is in neutral. So what I have to do is first I have to convert it into gaseous form. So after converting it into a gaseous form, I need to take out the electron from it to make it Na plus in gaseous form. So if I'm trying to convert solid to gas, what kind of energy we have to give? That energy is known as energy of sublimation. Now, after taking out sublimation, I'm trying to get converted when I'm trying to take out one electron. This particular energy is known as ionization energy. And because I'm taking out one electron, or the first electron, that is known as ionization energy 1, or first ionization energy. This is the definition of ionization energy. Now let's come back to the thing, how the things happen. Now, for example, I'm taking a product. I'm saying that A is something. From this, I took out an electron to make it A plus. Now, so for this, what is there? For this ionization energy, I represent it from ionization energy 1. Now, A plus, from this again, I'm still trying to take out. Somebody is already hungry. I'm trying to take out electron from. I'm trying to take food away from him or her. So I'll write what? This is ionization energy. Now next, still what I do is still I said what? No, I still want more. I'll take out 2 plus 1 more electron. I'll try to take out of it, and it will become. So now if you see that, it is obvious from this trend that ionization energy 3 have to be highest than ionization energy 3 have to be highest than ionization energy 2, and it has to be highest than ionization energy 1, because initially, yeah, okay, fine, it was neutral, it is ready to give one electron, but it's already a cation, and from that still it is hungry for the positive negative charge, and still you are trying to take negative charge from it. So the problem starts there, and that's why this is always true. This is always true for anything, that ionization energy or successive ionization energy will be always higher from the preceding ones. Okay. Next, when I'm discussing about ionization energy still, let's go for the trend. Either we can move from left to right or we move from top to bottom. So again, left to right, clearly, what happens to the atomic size? Atomic size, what is happening when I'm moving left to right? It decreases because it is more compacted. The bond will be more strong. To release electron, it will be hard. So ionization energy increases because this is more packed. Now here, what is there? They're already away from each other. Atomic size is high. They already have fight in between. They are ready to leave. So atomic size is more. So because of that, ionization energy is less. This is normal trend. Reason again same, atomic size why it is less, Z effective thing. Atomic size why more, cell numbers thing. Okay, so there is no discussion and I'm talking about that. Problems are where exceptions. So we have exceptions here as well. Number one. Now what we read that when we are moving left to right, size should decrease. So what we read, but helium is there here. So we just read that helium or neon or inert gases, they will have highest or they'll have maximum size. If size is maximum, say if size is maximum, so if size is maximum, so ionization energy should be minimum, normal trend. But what is the exception? They, when I'm talking about this one, inert gases, inert gases, they have ionization energy maximum in respective period. Maximum in respective period. Now problem arises here again. I'm saying that here size is biggest. They should be ready to leave it. Problem is what? Inert gases, they don't want to leave electron. Why they have to leave electron? They don't want to react. They want to stay like that how they are. They don't want to leave electron or they don't want to gain electron. We are just disturbing them. So because of this is not ready. It is very hard for someone to take out electron and make them react. So that's why the reason. That's why inert gases things become very important. First thing. Second exception. Now when I'm writing second period, so say I'm writing second period elements. So in second period element, what are the elements there present? We have lithium, we have beryllium, we have boron. After that, we have carbon. After lithium, beryllium, boron, carbon, we have nitrogen, we have oxygen, we have fluorine. And then the last obviously will be there, which is your argon or neon, sorry. So now lithium. What is a normal trend? When I'm moving from left to right, size decreases, so it should increase. This is what happens. But there is a small switch. You have to leave one, then you have to alternate, make it in this way. Then you have to leave one, then alternate in this way. So normal trend is changed to first will be what? First will be lithium, then will be boron, then it will come beryllium. Then what will happen? The next one will go carbon, then oxygen, then nitrogen, then fluorine, and for the last is neon. Now, why this trend? Why this? You can see there is small switch over here. Why boron came before beryllium? If you see properly about their configuration, so here there is no problem. This is 1s2, 2s1. Here, if you see this is what? This is 1s2, 2s2. Here, what is there? This is 1s2, 2s2, 2p1. So this is text. Now here when I'm writing, this is what? 1s2, 2s2, 2p2. I'll write this 2s2 here. This is 2p3. And what is here is 2s2, 2p4. What is happening over here is, if you see properly, in this place, what this is s orbital. S orbital is fully filled. In this place, what is there? This is p orbital. P orbital is half filled. Half filled orbitals or fully filled orbitals are more stable. When something is more stable, they're not ready to lose energy easily. So that's why this problem arises. And because of this only, this disturbance happened. Because of this full filled and because of this half filled orbitals here, s orbital which is fully filled, s can have maximum 2, it half 2, p can have maximum 6, it half 3, that is half filled, this is fully filled. Because of this difference, what happened, there is a small change observed in this. The same thing is being observed in the third period as well. Okay, in third period as well, you can find the reason will stay same for this. What will happen here is sodium will come first, then aluminum will come. Exact same. Under carbon, which one comes? Silicon comes, silicon uride. Under oxygen, which comes? Sulfur comes. Under nitrogen, which comes? Phosphorus comes. Under fluorine, which comes? Chlorine comes. Under neon, which comes? Argon comes. So this is a normal type. Okay. So this is an exception, which is number 3. Okay. Now next, when I'm talking about the next one, this is there. The reason this is there. Next one, next question in this is, what happened to the next exception? The next exception is very important. Fourth one, if you say. Now let's take example for the first ionization energy. Say I'm talking about beryllium and I'm talking about boron. So what I'm writing is, for beryllium, the configuration is what? 1s2, 2s2. For boron, what is there? It is 1s2, 2s2, 2p1. So when I'm doing what is, I'm taking out first electron here, I'm writing it as IE1, and after taking first electron, it is 1s2, 2s2. And this case again, I'm taking out the first electron, and the configuration changes to 1s2 and 2s2. Further, what happens is, now I'm taking out one more electron, IE2, it becomes 1s2 and 2s1. Now, sorry, after I did mistake. After taking out one electron, here left out will be how much? Here left out will be 2s1. Now further, when I'm trying to take one electron, it will become 1s2. Here from this one electron, so it became 2s2. From here, if I'm trying to take, it will be IE2. That will become 1s2, 2s1. Now, what is there in this case? If you see, what I write is ionization energy number 1 trend. If I write, that will be what? It will be more for beryllium, IE1, compared to boron. But in this case, if I write the IE2 for boron, it will be more when it is compared to beryllium. The reason is what? If you see electronic configuration, this is fully filled here. This is normal in general, this thing. After it loses one electron, it becomes half filled. But after this loses its electron, it will become full filled. So we know that half filled is stable, but from half filled, which one is stable? From half filled, which one is more stable? Fully filled. So because of this, this thing is observed. Okay. We'll go to the next trend, which is observed in boron family just now, which we discussed, boron, aluminum, gallium. So what how to try to remember it, you just try to draw a W, not the normal W. Try to draw a W with this thing. Okay. And normally how the electrons or how the elements are arranged, the first one is boron, so I'll write boron, then I'll write aluminum, after aluminum is gallium, then is indium, then is thallium. So if I'm trying to write the configuration, so what will be there? It's normal will be boron, after that boron, which one? See, you just draw the line, after boron, then this will come, and gallium, then which is coming aluminum, then which is coming is indium. So boron, after boron you'll write TL, then you'll write Ga, then you'll write Al, and then you'll write IM. These all are exceptions. These are not forming the normal trends. That's why I'm taking time and trying to explain you this. Now, next one is, this is 3. The last one for you is electron negativity. Now, electron negativity is what? This is normally, this is a scale. This is measured on a scale, how one particular electron can pull the other one. So it's on polling scale. Now, polling scale says what is? They have given a certain numbers. They have given you a certain value. Electronegativity is basically what? It's a tendency of the definition. If I want to write for electronegativity, I'll say it was tendency to attract shared pair of electron, So shared pair of electron, it tries to attract. It is given by Pauling scale. Electronegativity is a unitless thing. It doesn't have a unit. Okay, in chemistry, We can say periodic property, only one thing is there which doesn't have a unit, that is electronegativity. According to Pauling scale, if you want to write, we need to remember these values as well. Lithium, beryllium, boron, then we have carbon, then we have nitrogen, then we have oxygen, then we have fluorine, and then after fluorine. So you have to remember the values, starting with the first is 1. Just add 0.5 to each. This is 1.5, this is 2, this is 2.5, this is 3, this is 3.5, and this is 4. First thing to remember. After this, when I'm talking about is chlorine, you can write it for chlorine. According to NCERT, if I'm trying to go, chlorine is 3. Okay. You can see chlorine and nitrogen are having same thing. Both are having 3. Again, you can remember that H and P, that is HP petroleum, hydrogen and phosphorus 2.1. And then after that, if I have one is that is CIS. CIS is basically when I'm talking about is carbon, iodine and sulfur, that is equal to 2.5. This much is supposed to be read so that you can compare which is having more electronegativity, and this will make your organic chemistry also kind of easy. So based on this, we try to incorporate the things. Okay, so this is normal trends. Okay, so yeah, so this is what is the normal things you're supposed to read in this inorganic part. Let's try doing few questions so that you can understand. We'll start with the periodic properties only, so that you can, the first question we'll try to do is, question is, say, compare size. Size is basically I'm talking about atomic radius. Okay, the first one is lithium, sodium, potassium. Number B is, we'll take it as neon, beryllium and boron. And then C, we'll take it as aluminium, boron, gallium and indium. Okay, try to solve. We'll start on doing the questions. Today's first answer, we have given lithium, sodium and potassium. Normal trend, good. Dipesh is right, the first one is right. Moving down the group, size increases. So lithium, sodium, potassium. Next. Beryllium. Okay, so the highest is, okay, correct. So boron is less than beryllium, then neon. Right, everyone? Because neon in that particular period, it will have highest, so highest. From left to right, when you're moving, size decreases. So boron will have less compared to beryllium. And this, so very good. The pace. Next one done. Last one. BGNALN. B is less. So saying boron. And then after that, boron, aluminum. So in the answer, this will be there. So you'll write in that. Boron, aluminum, and gallium will have almost same. And then indium. Good, Sunil. Okay. Next. Good one. Questions done. Okay. Try next. Let's try next question as we have this things. N3 minus, F minus, Na plus, Al3 plus, Mg2 plus O2 minus. We need to arrange them in increasing order of size, ionic radius. Number B, say I have S2 minus, chlorine minus, K plus, Ca2 plus, and P3 minus. This is what is the two thing we are supposed to arrange in increasing radius. Okay. See if you're checking correctly, these all are isoelectronic species. Only thing you have to know is isoelectronic species means size is inversely proportional to the atomic number. Here you just write the atomic number. This is 7, atomic number 9, 10, 13, 12, and 8. So whose size will be less, whose atomic number is most. Atomic number of Al3 is most. Then comes Mg2 plus, then comes Mg2 plus, then comes Na plus, then comes F minus, then comes O2 minus, and then comes N3 minus. Similarly, in this case, if I want to write for sulfur, it is how much? 16, 17, 19, 20, 15. So whose size will be most? Most, this is smallest. P3 minus most. After P3 minus, it will be S2 minus, then Cl minus. After Cl minus, it will be K plus, and then it will be Ca2 plus. Okay, so this is isoelectronic species thing. Okay. Next, we'll do question based on ionization energy. Need to compare ionization energy. Number one is beryllium, nitrogen, carbon. So you are teaching in Jain also. No, I am just related with, uh, you can see Pratyush Academy. So I'm a teacher at Pratyush Academy, and again I teach in one more very reputed institute, but I can't share the name of that. We are not allowed to do that. Okay. We have Academy, Pratyush Academy at Bangalore. Yeah, this is, you have to compare the ionization energy. Okay, first answer we have NCB. Beryllium, carbon, nitrogen, two answers. Variation in answers. Beryllium, nitrogen, carbon. Why NCD and why BCN? See, when we are moving left to right, tendency changes, ionization energy changes. Say more than beryllium will be carbon, more than beryllium will be carbon, and less than and more than beryllium will be more than carbon will be nitrogen. I have given you B, N, and C. I see the exception which you have. You check. We have to leave what is first. Lithium is left, then beryllium, and after beryllium we have which one? We have boron. Then after that carbon is left, and then we have nitrogen and oxygen. The switching happens where? Here. So I'm giving you which one? I've given you this one beryllium, I've given you nitrogen, and I've given you carbon. So if you see here, beryllium is going on this side, but carbon is not being touched. Nitrogen is going this side. So this there is no changes in this, right? Only this carbon. I have to compare beryllium, nitrogen, and carbon. Beryllium, nitrogen, and carbon. Okay, next one. Beryllium, carbon, nitrogen. Yes, Dipesh have answered. Okay. Next one. Faster. More question will help all of us. So next question. Okay, we have answers. Answers we have is for ONE, we have ON in this. Then we have strontium, then we have calcium, then we have magnesium, then we have indium, then aluminum, and then gallium. Anyone different answer? Anyone have a different answer? Here any have to be have most, then N, then O. I think this is fine. Then next is we are comparing between magnesium, calcium, and strontium. So magnesium will have more than calcium, then strontium. Okay. And I'm comparing this. Gallium will have more than indium, thallium more. Okay. So all good. If this all is right, I hope everyone got that. Okay. Next, let's try some questions now. Let's try to. Okay, we need to compare the element having greatest difference between the first and second ionization energy. You need to find out the difference between the first ionization energy and second ionization energy is highest where. The questions are calcium, then we have B is strontium, C is barium, and D is potassium. Okay. So Jen says B, scandium. Okay. You should know the number. This is calcium. How you know about the barium? See, barium is which family? Okay, so this is group 2. Group 2 is what? The first one is what? So BEMGCASCBA. So you know this is from here to here. If I'm going, there will be addition of 10. So 4 or 12. Then 8 will be 20. Then after scandium, sorry, strontium. Okay. So this will be then after this we go to this becomes 38, and to 38 we are supposed to add how much? We are supposed to add 18. So 40, 58, 48 and 8, 56. So this is what is atomic number here, 56. The magic numbers we say them 2, 8, 8, then we add 18, 18 like this. We try to move on. Okay, so addition of after you add after from this to this, we'll add 4 to 8, 8 to 12, 8 again, 18, then 18. And after that, we go 32, 32. So that is not needed. This is 19. If you know this, you'll be able to solve this question. We are supposed to know this. Is just try to read few atomic numbers, which will help you more. Okay. Let's try few more exact questions. Okay. We have a question. Which of the following is correct? R radius ionic is directly proportional to Z, is directly proportional to Z effective. It is directly inversely proportional to Z effective, and it is directly proportional to Z effective square. Okay, that is what is the question. Ionic radius. Ionic radius is proportional to what? Okay. What happens when your effective nuclear charge? How that is related? When Z effective is mentioned, never tick something, any option which is related to Z. Whenever there is Z effective in the question, never try to tick anything which is related to Z. Z effective is more appropriate when we are talking about atomic number. So yeah, how this is interrelated. Z effective. What happens to ionic radius? Z effective term comes where? If you it should strike in your mind, Z effective comes when I'm moving from left to right. What happens to Z effective when Z effective increases? Z effective increases. Ionic radius, what happens to the ionic radius or atomic radius? It decreases. So how it is related? It is inversely proportional. So option, this has to be correct. Right? In this, see, the questions comes is very direct, very easy, and very scoring. If you know it, it's okay. You score it. If you don't know it, you leave. You lose the marks over there. It's very the best correct. 1 by Z effective. Let's try the next question. Next question says is which set of the elements have strongest tendency to form ion? Strongest tendency to form anions. And ions means what? Negative charged particle. Options says is NaClAl. Sodium, chlorine, and aluminium. Next one says is what? Copper, silver, and gold. Augmentin, okay, argentum and aurum. They are their Latin name. We can use the Latin name as well. Argentum and aurum is the name for silver and gold. Next is beryllium, fluorine, and nitrogen. Next one is which set, we're talking about the set, which set will have tendency to form strongest anions. And ions means negatively charged. Yeah, go ahead. Bottom says D. D is right answer because halogen group number 17, they have valency of what? -1. All of them will have show valency of -1 because their outermost shell, they have how many electrons? 7. They have a strong need of 1 electron to complete their octet. So to complete their octet, they need 1 electron, and for that, what they do is they take 1 electron. So they have a strongest tendency for this. Okay, good. Next one. Okay. Next question is, you need to, we have already done it though. Okay, so we'll not skip that, which we have already done. The correct order of electronegativity. You need to find out correct order of electronegativity. We have F greater than N greater than P greater than O. This is option question. This one is option A. Option B is F greater than O greater than P greater than N. Number C is F greater than O greater than N greater than P. Number D is N greater than O greater than F greater than P. Bottom says D and then he changed the answer to C. So bottom's answer is C. C answer is right. Bottom's this previous answer he have given D. That was also correct. This is also correct. Both is correct. Okay. Next question is they're asking you which among the following is the electronic configuration for most electronegative element? Number A is 3s. Okay, this is 3s2, 3p5. Number B will be 2s2, 2p5. Number C will be 4s2, 4p5. Number D is 2s2, 2p4. Which among this is an configuration for most electronegative element. They have not written the previous one, they have written only the final. So they have previously filled, then come to final one. Number B, again Gautam. Others are not solving. Gautam, you are correct. This is for fluorine. Fluorine is basically which one? Fluorine's electronic configuration is 1s2, 2s2, 2p5, and fluorine undoubtedly is the most electronegative element of full periodic table. Good. Next question. Next question is you have to find out which have the highest first ionization energy. And this is which is having the first highest ionization energy. The configuration given is 1s2, 2s2, 2p4. Next is 1s2, 2s2, 2p3. Next is 1s2, 2s2, 2p2. Number D is 1s2, 2s2, 2p1. Which will have the highest first ionization energy. Jain and Gautam. Sujan says B, Gautam says D, Komal says D. Okay. Good. So first ionization energy. The base says D. Okay. This has to be the correct answer. See, because this is half filled here. So half filled first ionization energy, this is what electron you have to take out. Here you have to take, this is not half filled, not fully filled, not half filled, fully filled, not half filled, fully filled. This is half filled. Taking out electron from half filled and fully filled is difficult. When you're comparing half filled and fully filled is more stable. So it's more difficult to take out electron from fully filled. Okay, good. Everyone starts trying, so it's good. Let's try next question. Okay, they're asking you which among this have the highest ionization energy. Number A is Na plus, number B is F minus, number C is Mg2 plus, number D is O2 minus. Which have highest ionization energy. Bottom says A. Have to first Durgesh says A. Okay. So these all are isoelectronic species. So first thing you have to see is atomic size is inversely proportional to, like, atomic size basically depends on what? Atomic number. So here atomic number, if I'm writing this is 11, this is 12, this is, I have another answer. The base is D. I have Sunil Pandave with C. Okay, 2, 8, 9. I'll just arrange which is, now all these are isoelectronic species, 10 electrons. So which is size is inversely proportional to atomic number. Whose atomic number is less? They're asking your highest ionization energy. So ionization energy will be highest for which is smallest. Which will be smallest will be Mg2 plus. So answer is C. Sunil is right. Which will have the highest ionization energy will be which one? Which have smallest ionization energy. Ionization energy means the size have to be small. Size small in the case of isoelectronic species, how I'll decide? Size is inversely proportional to atomic number. So whose have 12 is the highest atomic number will have the smallest size. Smallest size means what? Highest ionization energy, unless and until we don't have exceptions. So Nil, right answer. Next what we'll do is, next question is, from which of the following species it is easiest to remove one electron? Easiest, or we write easy to remove one electron. Remove one electron. Options are O, B, O2 minus, C, O minus, C is O plus, and D you take it as O minus. From where taking out, removing one electron will be easier? Easiest to remove one electron. Sujan says B. So Neil says B, Gautam says B. Okay. So where electrons will be more, that will be easy to take. Answer is B. Size is bigger, so it will be ready to lose it easily. Okay. Next. Okay. This is good question. What they have given you is, they have given you ionization energy 1, ionization energy 2, ionization energy 3, ionization energy 4, ionization energy 5 value. That is 7.1, 14.3, 34.5, 46.8, 162.2. Everything is in electron volt. 7.1, 14.3, 34.5, 46.8, 162.2. Which, this shows which particular atom. Options are A, SI, F, C. This particular, this is what, this is ionization energy 1, ionization energy 2, ionization energy 3, ionization energy 4, ionization energy 5. So this, which you feel is represented by this particular trend. Gautam says answer is D. No, Gautam says D. Gautam says D. Gautam says answer is D. Name another answer. In this kind of question, if you are not very much sure, just see that you have number. The sodium is what, 1s2, 2s2, 2p6, 3s1. But talking about silicon, it will be how much? 1s2, 2s2, 2p6, 3s4, 1s2, 2s2, 2p5, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This is calcium. Okay, so you write down this thing and then you see now what they're telling is ionization energy 1. So this is gone. From here, if I'm talking about ionization energy 2, so 5. Ionization energy 3, so 4. Okay. Ionization 1 gone, 2 gone, 3 gone, 4 gone, 5. So ionization energy 1, 2, 3, 4, and 5. Now, so you can see there is only what is there. You have to observe this. There is what, there is a highest jump. So that means it has to be something which is very stable. That's why they are showing this thing. So here what was there? It is 2p4 to 2p3, the fourth one. Here if I'm talking about, it will be ionization energy 1, so 3, ionization energy 2, so 2, ionization energy 3, so it will be 1, ionization energy 4, so okay, I wrote 3s4 here. This is blunder. What is this? This will be on purchase. 1s2, 2s2, 2p6, 3s2, 2p, 3p2. Okay, silicon, right? No, silicon is 10, 1s2, 2s2, 10, 12, 14. Okay, fine. So I'm talking about this. So from here it will go 1, ionization energy 1, ionization energy 2, then from here ionization energy 3, then ionization energy 4. Now you see it is, when it is, this one becomes 0, this is 2p6. Now from 2p6 it have to go to 2p5. So from fully filled orbital, you're supposed to take one electron. That's why you are seeing this huge jump. Here also you see one, when you are taking out one electron, so this two goes, and from here what it goes is, it goes to then 5, then 4. The 4 to 3 it have to go. So this much huge jump you don't have to get. Now here also if you go, it will go from what? It will go 4, then it will go 3, then it will go 2, then it will go 1, and then it will become 0. From 1 to 0 it will go. There is not huge jump, not expected. Here you see the huge jump is expected, so the answer has to be silicon. Wherever you find, conclusion is wherever you find half filled or fully filled orbital, to counter attack that you need more energy to take out electron. So that's why that will be probably answers in this kind of questions. Okay, next question we'll do is, which of the following electronic represents okay, which of the following represents noble gas configuration? So the option 1 is NS2 NP6, which is representing noble gas configuration NS2 NP6. Option B, we'll take it as NS2 NP5. Number C is NS2 NP64, and then we'll take NS2 NP3. Which among this represents the noble gas configuration, noble gas electronic configuration? Which among this? Okay, Sunil, Gautam have given answer. Both have given answer as say NS2 NP6 8, because both are same shell. They should have 8 electrons in the outermost shell. Here it is 7. Here it is 6. Here so this is the only option. Good. We'll do one last question. We have still time. Which among the following ions have the highest value? Highest value for ionic radius, highest value for ionic radius. Okay, so first one is lithium plus, second one is beryllium 3 plus, third one is O2 minus, fourth one is F minus. Which among this have the highest value of ionic radius is the question. Highest. So Jen says C. Sunil says C. Sujin says C. Okay. So which will be having ionic radius here. So first of all, when I'm talking about ionic radius, this will be what 3, this is 3. Atomic number I'm writing 3, 5, 8, and 9. So if you see the number of electrons here, this is 10 and this is 10. So these two are isoelectronic species. Anyway, ionic, when I'm moving, this is left to right when I'm moving. Obviously, ionic radius, it has to decrease. So that is okay. So that when I'm moving from left to right, the ionic radius value. So this is 3, this is 5, and I'm comparing this to which have lesser. So this have less, 8. Okay, so I'm talking about this is 8. I'm talking about 8 atomic number, inversely proportional. Ionic radius will be more. So good answer. Sunil correct. Sujan correct. Answer will be C. So good. Okay, fine. So this was the session for today, where we were covering inorganic chemistry. There's another session which is going to come for inorganic chemistry. It will be related to other part. Okay, so thank you. We are done for today. Thanks for joining, everyone. Have a nice day, or you say have a nice good night. Okay, bye. Thank you. All the PDF, everything will be shared once the sessions are over. Don't worry. Bye. Thank you.